torque and equilibrium. Start this song by telling them how to solve each term and give their given definition. When torque is away, the force of an object displayed, and measure how much of the force causes it to rotate. But when the force is positive, it rotates counterclockwise in a clearly shown phenomena that is until it's stopped by an opposing force and a negative torque. Now let's look at an equation to see how it works. Torque has an equation, but it's harder than it may seem. It's force times the distance from the axis of rotation. If you're a beginner, first make sure it's perpendicular, and if it were administered a bit further from the distance were diminished, your results would not be similar because the integers have changed. The answer's not the same, so get it through your brain. And if you get it, now you won't be lame. The distance from the axis has decreased, which means the resulting force has ceased to be as strong as it would be if it were further from the axis rotating. So next time you're asked about torque, get it right. My rap about torque is just something light, but equilibrium is just as tight. So 2D sag, I pass the mic.
Now let's talk equilibrium. This occurs under the conditions when there's no net influences. Ding, that's cool, my friend. In the real world, this is important to discuss the unknown force which is required to support such things as cars on a bridge. If there is a zero net force and there is a zero net torque and the right equals the leftward up with downward, then you have found it. Dang, that's lit. Wait, have we even told them this stems from Newton's law of motion, that if force
Sine
is
50
not
degrees
opposing
equals
and
the lever arm
orbital
over
force
0.28
is
meters.
remaining the
To
same.
solve for the lever arm, you multiply both sides by 0.28
Solve
meters
this, you
to
must
find
a
that the lever arm
place in
equals
which the
0.21449.
axis is rotating,
Then you
and
use all the
then
information we
using
have
this
and plug it back
equation,
into the
find
original
the
torque
answer
equation.
by
Torque
just
equals
making
force times the lever arm.
X, force of
With this
Y,
information,
force
it
of
is
torque
45
equals
newton meters
zero.
equals
Nice.
force
Now
times
that we've taken
0.21449.
both
To
terms
solve for
and
force,
solved
you
them,
divide
let's try
45
working
newton
out
meters
a
by
problem.
0.21449, and you find that the force is equal to 209.79
I don't
newtons.
even care.
Although net external force can be held responsible for linear acceleration, net external torque is the cause for rotational acceleration. Torque depends on quite a few things. It depends on the magnitude of the force applied, the direction of the force, and the exact place where the force is directed in relation to the rotational axis. If we push a door with a small force versus a large force, the large force causes the door to open much more easily. In addition, it's much more difficult to push the door near the axis of rotation rather than towards the end, away from the hinges. Now we know we keep saying axis of rotation, and you're probably wondering what that is. Well, the axis of rotation is the center around which the rigid body rotates. Now in the case of the door, the hinges would be the axis of rotation because that's what our door rotates around. When dealing with torque, there are two important terms you should know: lever arm and line of action. The line of action is collinear to the line of force and extends to show the direction of the force. The lever arm is drawn between the line of action and the axis of rotation. It is always drawn perpendicular to both and is there to illustrate the distance between the two. You're installing a new spark plug in your car, and the manual specifies that it be tightened to a torque that has a magnitude of 45 Newton meters. Using the data in the drawing, determine the magnitude of the force that you must exert on the wrench. This is the data we are given. This is the position of our wrench, and this is the direction of our force. We're given a 50-degree angle and the fact that this portion of the wrench is 0.28 meters. Now we must identify the axis of rotation, line of action, and lever arm. The line of action is collinear with the force, which means it's right here. The axis of rotation is here because this is the point the wrench rotates around. Lastly, we know that the lever arm must be perpendicular to both the axis of rotation and the line of action, which means the lever arm is right here. In this problem, we're solving for the force, but we're only given the torque, so we must find the length of the lever arm. To find the length of the lever arm, we will use the 50-degree angle and the 0.28 meters we are given.
Sine of 50 degrees equals the lever arm over 0.28 meters. To solve for the lever arm, you multiply both sides by 0.28 meters to find that the lever arm equals 0.21449. Then you use all the information we have and plug it back into the original torque equation. Torque equals force times lever arm. With this information, it is 45 Newton meters equals force times 0.21449. To solve for force, you divide 45 Newton meters by 0.21449 and you find that the force is equal to 209.79 newtons. Equilibrium is when the magnitude of torque is zero. A real-world example of this that can be easily seen is when people use a seesaw. With the seesaw, as each person sees and saws, the torque changes as each person goes up and down. But when the seesaw is level, the torque equals zero, thus putting the seesaw at equilibrium.
Torque and equilibrium are directly related. As stated before, equilibrium happens when the rotational motion of the object does not change. This means the net external torque being applied to the object is zero.
A uniform meter stick supported at the 30 centimeter mark is balanced when a 0.5 Newton weight is hung at the 0 centimeter mark. What is the weight of the meter stick itself? First, we draw our meter stick. This is the 50 centimeter mark. We know that the meter stick is supported at the 30 centimeter mark. We also know that there is a weight that is 0.5 newtons that's hung from the 0 centimeter mark. Now we know that the weight of an object comes from the center of it. Therefore, the unknown weight of the meter stick will come from the 50 centimeter mark. When we're doing equilibrium problems, we treat the fulcrum, or the thing that the meter stick is balancing on, as the center. And any object that is going counterclockwise towards the center is considered a positive. Anything going clockwise is considered a negative. So when we solve an equilibrium problem, we're finding the sum of the torques, so we add all the torques together. Because weight 1 is rotating counterclockwise, it will be considered positive. So we multiply weight 1 by the distance from the fulcrum. Now weight 2 is rotating clockwise around the fulcrum, which makes it negative. Therefore, we subtract weight 2 multiplied by its distance from the fulcrum. Equal that to 0. Now we get to plug in our variables. For weight 1, we know that it's 0.5 newtons. And its distance from the fulcrum is 30 centimeters, or 0.3 meters. Now we subtract weight 2, but since we don't know it, we'll leave it as a variable. And its distance from the fulcrum is 20 centimeters, or 0.2 meters. And make this all equal to 0. Now to make both sides positive, we add weight 2 multiplied by 0.2 meters on the other side. So now we have... Okay. When we multiply these two together, we find that the answer is 0.15 Newton meters. On the other side, we still have weight 2 multiplied by the 0.2 meters. But if we divide both sides by 0.2 meters, we find that weight 2 is equal to 0.75 newtons.
What the heck just happened?